We'll also talk about the resolved star formation, but resolved in a much smaller scale. So I'm going to talk about the clump in high redshift star-forming galaxies. So this work has been done together with many CANDELS members, and most of them are in this room. So here are examples of high redshift star-forming galaxies, and those purple circles are the clumps that I'm talking about today. So here are more examples of clumpy star-forming galaxies at redshift from 1 to 2 to 3. And those clumps are mostly seen in rest frame UV and optical images. They are also seen in emission line maps, for example, H-alpha map. And we can find those clumps spanning a lot wide redshift range at 0.5 to 5. And the typical stellar mass is 10 to 7 to 10 to 9. And the size is about 1 kiloparsec or less. We know those clump regions, they are blue. They have higher specific star formation rate. And many of those clumps are found in rotation disks. And this is based on both morphological and kinematic analysis. They are not just a remnant of merger. So why should we care about those clumps? Because they are important tests of our understanding of star formation feedback and galactic structure formation. We want to know what is the formation mechanism of those clumps. Are they formed due to violent disk instability? That means they are formed in situ, or are they formed due to minor merger, major merger? Both are ex situ process. And once they formed, how are they going to evolve? And are they going to form the progenitor of today's sparge when they go into the center of galaxies, or they are just quickly disrupted by feedback? And if that is true, what kind of feedback do the work? Is thermal feedback or non-thermal feedback? And also we are curious about, is there any connection between clumps and the AGN supermassive black hole? So today I'm going to first talk about the clumpy galaxies in CANDELS images, and I'm going to focus on two parts. First is the basic demographics of clumps. How many star-forming galaxies at high redshift contain such clumps? And the second is the detailed studies of the physical properties of those clumps. So first is the clumpy fraction, meaning how many star-forming galaxies contain such clumps. We have figured out a way to define clumps in objective and less redshift dependent way. That is, we define clumps as discrete star-forming regions that contains at least 80% of the total UV light of their galaxies. We believe this definition is objective. It's more objective than any visual inspection, and also it has smaller redshift dependence. And if you assume this definition, then we can do a simple number count. And we found at redshift 2.5 or higher, about 60% of star-forming galaxies contain at least one UV bright off-center clumps. And this fraction changes with redshift. Also, it depends on the stellar mass of galaxies. For massive galaxies, when you go to lower and lower redshift, the clumpy fraction drops quickly. At redshift 0.5, only 15% of galaxies contain such clumps. For intermediate galaxies, it also drops, but slowly. At redshift 0.5, you still have 40% of galaxies contain such UV clumps. And for low mass galaxies, always like constant. You always have 60% of galaxies have clumps. And since we know this clumpy fraction, we can compare the clumpy fraction to different model predictions. So we found that the VDI violent disk instability predicted the clumpy fraction of massive galaxies very well. Here, massive means galaxies greater than 10 to 10.5. But the VDI underestimated the clumpy fraction of intermediate mass and low mass galaxies. For those galaxies, you need something else to form clumps. We believe that minor merger could be a very possible way to form clumps. When we compare the minor merger fraction here, it more or less matches the clumpy fraction at low redshift. So minor merger could be the reason to form clumps in intermediate mass and low mass galaxies. And we can basically rule out major merger as a main reason to form clumps, because the major merger fraction is way lower than any clumpy fraction. Then we pick up 10 galaxies from HUDF, where we have the deepest rest frame UV and optical broadband images. And we measure star formation rate and stellar mass of each clumps. And here is the star formation rate versus stellar mass relation. red are clumps, and blue are disks, and black are integrated galaxies. So you can see from that plot, the majority of star formation rate is still happening in disks, but the clumps, they have higher specific star formation rate. The normalization of clumps in this plot is higher than the normalization of the disks or galaxies. So that's what we said before. Clumps, they are blue, they have higher specific star formation rate. What's interesting is here, we find the color gradient of clumps. Clumps close to the center, they are red, and the clumps close, in the outskirts, they are blue. So of course we have SED fitting, we can convert this color gradient into the gradient of different stellar population parameters. We find the clumps in the center, they have less star formation rate, and the clumps in the center, they are older, they have a little bit more dust, and they are much denser than clumps in the outskirts. So these results are consistent with what Neil Mandelker found in his in the Vela simulation. In that simulation, they also find the age gradient. Clumps in the center are older, and the clumps in the outskirts are younger. So we conclude that our result is actually consistent with the inward migration scenario. That means clumps is an important way to form barges. Clump will go into the center of galaxies and merge to form the progenitor of today's barges. Now I'm going to switch to the second part of my talk, this Clumpy Galaxies in CANDELized image. So the goal of this part is to understand what can we detect from CANDELS images, and second is what do we actually detect from CANDELS image. So a CANDELized image is the numerical simulation plus observational effect. Here we start from the art simulation from Joe Brimark and Daniel Sabarino's group, and the resolution is very high, about 30 or 25 parsecs, and all those simulations are processed by Sunrise to calculate a radiative transfer. So now we have the light image of each band. So for each band, we add CANDELS observational effect to those high resolution images. We downgrade the resolution, we add PSF effect, and we also add noise. Here's an example. This is one snapshot of galaxies, and this is a face-on view, this is edge-on view. Here we have 4 panels, V, Z, J, H. Those are CANDELized image of this high resolution image, and all matched to the CANDELS observational effect. So here we focus the generation 2 of or generation 3 of Vela MRP. In this simulation, this simulation contains both supernova feedback and radiative pressure feedback. So this simulation matches the stellar mass relation better than you only have supernova feedback. And the stellar mass in this version of simulation is a little bit low, so they are around stellar mass 10 to 10. So we have this simulation, and we run our clump finders in 2 ways. First, Neil Mandelker ran his clump finder in 3D gas map and the young star maps from the simulation snapshot. So those purple squares are Neil's clumps, and also I run my clump finder in the CANDELized V-band images, and the yellow circles are my clumps. And when you overplot my clumps with Neil clumps, you can immediately see 2 things. First, my clumps only covers those larger clumps from Neil's clump sample. And the second is some of my clumps contains at least more than 1 clump from Neil's sample. The 2 points are not surprising because they are the result of the sensitivity and resolution limitation. So, but the important thing is to which extent we understand those 2 effects. So to do that, Neil and I run our clump finder in 4 galaxies from redshift 3 to redshift 1. We show the clump number density, clump number distribution. Dashed line is the result from Neil's clump finder, and the solid line is the result from my clump finder. When you take a ratio between the solid and the dashed line, you can get this detection probability. So that tells you for a clump with given property, what is the probability to detect it from CANDELS like images. So here, if you look at the probability distribution as a function of a star formation rate, you can see a very clear redshift dependence. High redshift galaxies, you can only detect them at highest star formation rate, and low redshift galaxies, you can detect it to a little bit lower star formation rate. But if you look at this star formation rate of clumps divided by the star formation rate of the total galaxies, the redshift dependence is much less than in this panel. So remember, in our first part, we talked about the clumpy fraction. We use a light fraction instead of absolute magnitude to define clumps. That is the first order approximation of the star formation rate of clumps divided by star formation rate of the total galaxy. So in that way, use this ratio is less redshift dependent way to define clumps. And also you can see if you want to sample that are 80% complete, so you can only count clumps with fractional star formation rate greater than 0.1. That means contain 10% of star formation rate of the total galaxy. If you want to sample complete greater than 50%, and the ratio is a few times a few percent of the star formation rate. So that same thing happens here. If you want to much complete sample, you can only have clumps greater than 10 to 8. But if you want a little bit less complete sample, you can go down to log 7.5 clump mass. Now we look at the second problem, is the blending problem. We know some of my clumps actually contain more than one clump from new sample. Here I show you the ratio UV luminosity of clumps divided by UV luminosity of galaxies. For my clumps as a function of redshift, each point is color-coded by its neighbor star formation rate contribution. So the neighbor star formation rate contribution means I find a clump and I have a certain radius. I go to the certain radius to see whether there are any other clumps from NEO's sample. If there are other clumps, then we calculate how much the star formation rate contributed by those neighbor clumps. So dark blue means you have zero neighbor contribution. Clumps are very well isolated. Green and yellow means you have 50 to 60% of star formation rate, or UV light is actually contributed by your neighbor clumps. So if we show a media of redshift and luminosity beam, you can immediately see a trend. When you go to low luminosity clumps and the low redshift clumps, they are quite isolated. There's almost no neighbor contribution. But when you go to high redshift and the bright clumps, you start to have lots of neighbor contribution. And here is again the plot of neighbor contribution. Here I plot also the medium of the fractional UV luminosity of clumps as function of redshift. So you can see clumps, they have lower fractional UV luminosity, and when you go at low redshift, when you go to higher and higher redshift, this ratio is getting bigger and bigger. So the point here is whether this trend is physical or it's just totally due to the blending of several clumps at high redshift. Because we know the neighbor contribution of each clump here, we can subtract the neighbor contribution of the UV luminosity. Then we got this trend. So you can still see a little bit increase towards high redshift, meaning the clumps at the high redshift, they still contribute more UV light to their galaxies than low redshift clumps. So that's still redshift evolution, and we conclude that it is intrinsic that high redshift clumps are UV brighter than low redshift clumps. So we use, as I said, we use the comparison between the clumps from high resolution images and the clumps from CANDELized images. We can understand the completeness of the clump detection that will help us to determine the clump luminosity function, mass function, and star formation rate function. We also know that the blending effect of clumps at high redshift that will help us to measure stellar mass, star formation rate, age, extinction of clumps. When we combine these two parts together, we can actually understand the physics behind the clump properties that measured from CANDELS images. So then we can understand the formation and the fate of a clump. So the important thing is you have to observe your simulations. You cannot just start from high-resolution simulation, because that's not what we can observe. We can only observe the images with all kinds of observational effects added. So basically, this is a summary of my talk. We studied the substructure of galaxies, and we studied clumpy fraction, clump properties. And what's more important, I want to draw your attention is to understand the structure and morphology of high redshift galaxies, you need to observe your simulations. And that's why we are starting CANDELized clumps. And this part of the work is still ongoing. So I hope I have new results soon. Thanks.
We have time for a few questions. Everybody's getting tired at the end of the day. Okay. If not, thank Yicheng again. And the last talk of
formation. We want to know what is the formation mechanism of those clumps. Are they formed due to violent disk instability? That means they are formed in situ, or are they formed due to minor merger, major merger? Both are ex situ process. And once they formed, and those purple circles are the clumps that I'm talking about today. So here are more examples of clumpy star-forming galaxies at redshift from 1 to 2 to 3. And those clumps are mostly seen in raster frame UV and optical images. They are also seen in images. We also talk about the resolved star formation, but resolved in a much smaller scale. So I'm going to talk about the clump in high redshift star-forming galaxies. So this work has been done together with many CANDELS members, and most of them are in this room. So here are examples of high redshift star-forming galaxy line maps, for example, H-alpha map. And we can find those clumps spanning a lot wide redshift range, 0.5 to 5. And the typical stellar mass is 10 to 7 to 10 to 9. And the size is about 1 kiloparsec or less. We know those clump regions, they are blue. They have higher specific star formation rate. And many of those clumps are found in rotation disks. And this is based on both morphological and kinematic analysis. They are not just a remnant of merger. So why should we care about those clumps? Because they are important tests of our understanding of star formation, feedback, and galactic structure.